Okay, then partial premixing. As I told you, we will now try to add some amount of air in the fuel stream. So, this is a burner. Again, you can see this is a coflow burner. Basically, there is a core and annulus region, and this is the region where we are trying to now only supply the the fuel here. LPG is used. Okay, LPG is used, and some partial premixing we are doing. So, now when I say 0%, 0%, there is no partial premixing, no primary air is supplied, only LPG is supplied at a given flow rate. Okay. The flow rate of LPG is kept constant in this. Okay. So, now you can see that smoke forms, tip opens and smoke forms. You can see that the soot is not able to oxidize within this formation region or in this region, and smoke forms here. So, we have selected a flow rate which is higher than the smoke point also, and you can see that the flame will result in a smoky flame. At the tip will show some smoke coming out of that. Now, I add 20% of primary air. You see that I am closing the flame, no smoke is there. So, that is the effect, and two more effects are there basically. One effect is the flame height is very high here. We can see a rapid decrease in the flame height. Flame height is reduced tremendously, and also the soot which is coming out as smoke in the earlier case here is now arrested, and there is no smoke coming out of the tip at all. Okay. Now, increase it further to 40%. Now, you have to note that the 40% is the not flammable. Okay, if it is around 40%, less than or around 40%, less than or equal to 40%, this is not flammable. The mixture is coming out of the port, no, fuel plus 40% primary air will not be flammable. So, this is what is 40% or less than 40% will not be flammable. This is limit. So, when you increase the primary air more than 40% approximately, then you will give flammable mixture, you get a flammable mixture. Okay. So, you have to note that the LPG air coming out of the core pipe is not flammable when the primary air content is less than around 40%. Okay, you can, when you say around 40%, you can also take 40% into consideration, and this is not flammable. So, you can see that 20 to 40%, there is a tremendous decrease in the flame height. Second aspect is, you can see the blue region. Blue region here is very small, because only at the base some air is available for it to burn. Now, due to the primary air, the blue region has extended to some height like this. Now, when you say 40% air, flame height has reduced and the blue region has increased, correct. Okay. Blue region height has increased. Okay. So, control of soot, control of extent, then better burning. When I see more and more blue regions, I am trying to we can see that the more oxidation has taken place. It is like a premixed flame, and we will have more control over this. So, after this 50% onwards, it is flammable mixture. Please understand that. So, you can see that not much change in the flame height. So, from this to this drastic reduction, from this to this drastic reduction has taken place. But after this, when it enters the premixed combustion regime, you can see the flame length is not much affected. Okay, the flame length is still here, also it is high here like this. So, flame is not much affected, because we can see that the laminar burning speed etc. will be the characteristic, no, not the flame extent. So, once if you burn in the diffusion controlled regime, then the flame length will be the important characteristics. When you go towards the premixed regime, then the laminar flame speed will be the important characteristic. You can see that formation of triangular flame inside here. A premixed reaction zone is visible, and also when you go to about 80%, you can see the premixed cone. So, these are all the characteristics. When you slightly add, but we will not do, so that is what this box is about. So, we will not consider these, because these are all flammable mixtures. So, these are normally not considered. So, we go for primary aeration which will have the mixture not flammable. Because if the flammable mixture exits out of the core flow, then there is a problem of flashback. So, when you have a problem of flashback, then we have to restrict your flow rates. So, that means that we cannot have the joy of operating the burner in a wide range of conditions, which is the benefit what we gain from a diffusion controlled flame. Okay. Now, let us see some aspects of effect of partial premixing. Basically, flame height decreases significantly. That is what we have illustrated here clearly. Flame height decreases significantly when you have partial premixing, and you can see that soot formation reduces and is oxidized within the flame. Second aspect. Okay. Now, when you increase this, third aspect is the blue region. The extent of blue region increases. Okay. So, here it is smaller, here the smallest, then it increases and it increases considerably. Okay. So, then premix flame forms. We do not really care about these positions, and you can see this. However, the main aspect is the reduction in the soot. So, we do not have any soot formation at all, that is soot forms and oxides within the flame. Then, as I told you, case of 40% air represents the limit of formation of premix flame. So, just higher than 40% you will get into the flammability limit. So, these are LPG flames. Considering LPG as a mixture of 60% butane and 40% propane by mass, okay, if you calculate the equivalence ratio for 40% of the stoichiometric value, primary air in the as 40% of the stoichiometric value, your equivalence ratio will be 2.5. So, that is a very rich limit. Okay. So, that is the limit. So, for the this combination of propane and butane, where it will not be ignitable. But if you go to, so it is just ignitable, we can say just ignitable. If you slightly decrease or slightly decrease the primary aeration, it will not ignite, slightly increase, it will ignite. So, this is the limit of the rich limit of this LPG for the primary fuel air mixture to be flammable. Next, if the primary air content is increased to 50%, now the equivalence ratio drops to 2, then you can see that the mixture will easily ignite without adding any more oxidizer. So, now what happens here? The secondary aeration is not required, it will burn. But anyway, if you see that rich mixture burns, then more CO and even COH2 also will be present in the products. Then anyway, you need additional air to burn it. Now, rich premix combustion starts, flame height does not change significantly. That is what I have told here. So, here the drastic reduction in the flame height is not seen in this. Okay, when you reach this. So, even here we are not supplied 100%, correct? We have 50, 60, 70, 80% of the primary air is supplied, that is not 100%. Even equivalence ratio is not 1 here, but you can see that the flame height does not change much. Okay. So, and at 80% primary air, the equivalence ratio is around 1.25. You can see clearly the inner cone, inner flame cone. So, that is the transition from the diffusion to the premixed regimes. But we will now stop. As I told you, when you want to operate the burner on diffusion mode, it is better to stop with this 40%, which is the limit of the formation of a premixed flame. Okay. Now, again these experimental results, numerically also we are saying the same effects. You can see that here LPG flames are numerically predicted. The orange contours show the temperature contours in Kelvin. If it is say 2000, the bright orange is 2000 and the white is about 300 Kelvin temperature. Okay. Now, other than the temperature contours, it is also shown the dark line which represents the stoichiometric contour line. So, stoichiometric contour line, that is the fuel plus the stoichiometric amount of oxygen. What is that in the, you know the fuel mass fraction and you know the mass fraction of the oxidizer. When they mix stoichiometric in proportions, what will be the locations where they mix like that. So, that locus is joined here and this contour line is got, and this is for example, this is 0% primary air, this is 10% primary air, 20% primary air and 40% primary air, and you can see this at 0% you have a flame which is now it's like a normal diffusion flame, but when you initially add 10% of primary air, you get a higher length. You can see this flame closes at a larger distance. So, flame length increases. Okay, initially with 10% of the primary air, you will see that the primary air, the volumetric flow rate of the mixture increases. So, it is not able to burn faster. So, because the air is not sufficient, the oxygen is not enough to burn within this zone, because the flow rate is also increased. So, due to the effect of increased flow rate and limited oxygen available, the flame length slightly increases initially. However, when you increase it to 20%, a drastic reduction happens in the flame height, and again to 40%, again there is a reduction in the flame height. So, this is the important thing we should understand about the characteristics of the flame, and you can see that the flame radius is not much affected in all the cases, almost the same flame radius, but the flame height initially slightly increases when you add. So, this is not the correct premixing to do. Do 20%, you get a good reduction in this, and again 40% it is reduced. But let us see soot. Okay, the primary aeration, even though slightly increase the flame length, that is not a big problem for us. What it does to the soot is what is important. So, let us see that. So, let us take these two cases first, 0%, 10%, and see how the soot behaves. So, for example, again numerically predicted soot contours we are given here. Please understand that soot volume fraction is the quantification which we do for soot. Okay, in a given volume, what is the fraction of the volume which has soot? That is soot volume fraction, and this is given in grayscale contour. That is, the black will be the highest soot volume fraction value, and white will be the lowest soot volume fraction value. So, the volume fraction basically like mole fraction, like let us consider. Then the lines, colored lines here are called soot oxidation rate, kg per meter cube second, soot oxidation rate. Again you can see the variation, the red lines represent 0.0018 and the blue line which is lowest is 0.004. So, both are shown here. This is for 0% primary air and 10%. We have just taken the first two cases to show and discuss here. In both you can see that soot is formed in this range, very small amount of soot is there. You can see that the soot forms here, and you can see the maximum volume fraction of the soot in this area here, and soot oxidation however occurs only in this region where the red is there, maximum soot oxidation, red and green let us take. So, in this region the soot oxidation is maximum. After that now the temperature anything is not much favorable for soot oxidation to proceed. So, what happens is the flame will leave some soot out. However, on the other hand, if you take 10% case, you see the soot oxidation red lines is extending nicely. You can see the red lines and green lines were very short. This finishes here, correct? In this regime, the red lines and green lines of soot oxidation are over when there is no partial premixing. But the 10% partial premixing, slight increase in the frame length was found, but the soot oxidation, green line and red line you can see now extends along the flame. That means the soot is going to be less. In fact, the soot actually reduces when you increase the primary aeration from 0 to 10%. Okay, but the maximum soot which is formed here, okay, and here they have same value 1.2 10 to minus 6, but we can there is a clear reduction in the soot because of increase in the soot oxidation rate with the primary air. So, that we have to understand. Now, we will take the other two cases, that is 20% primary air and 40% primary air cases. Okay. So, now I need different scales to plot it, because if you see 20% primary air, the maximum soot volume fraction is 5 into 10 power minus 7. When I go to 40%, it is 1 order less in magnitude, 7 into 10 power minus 8. Similarly, you can see the soot oxidation rate, which was 0.0008 for the case of 20% primary air. It has reduced significantly to 0.00017 4 times, less than 4, more than 4 times it has reduced. Okay. Now we can see when compared to this 1.2 in 10 power minus 6, already for 20% 1 order of magnitude lesser, 40% again it is 1 magnitude lesser than the 20% case. And soot oxidation rate also you can see here 0.0018 reduces to 0.0008, reduces further to 0.0017. So primary air is very important, and please understand till 40% I do not have premixed mixture, that is it will not flame ignite. Okay. So by just adding 20% or 30% or 40% primary air, I can abate the soot formation completely. So that will give us good control. So we have seen the reduction in the flame length, So that means we can go for primary aeration. As if we want to reduce the flame length, we can go for primary aeration, which will significantly reduce the flame length. Then you have here the soot formation decreases, soot oxidation increases with a little amount of primary air, 10% of the stoichiometric value. You can see tremendous increase in the soot oxidation, and the soot formation, because of this increased soot oxidation, soot formation decreases significantly. Okay. So 20 to 40% the soot goes almost to a very low value. So when you slightly increase it to 40%, then you do not have any soot at all. It actually goes exponentially to a very low value. Okay. Now we go for cross-flow diffusion flames. The cross-flow diffusion flames basically, as I told you, the fuel is supplied in a horizontal injector, and the air is supplied in perpendicular to this fuel stream or parallel to the injector. Okay. So now again these two photographs are LPG and air cross-flow flames. We can see that LPG is sent through horizontal injector. So some injector means you can consider a honeycomb structure or a porous plate through which uniform injection of LPG is possible. So the velocities will be uniform over this injection the plate, and this is top view of the flame, and this is the front view of the flame. You can see that this is injector. So this injector position, again here also the injector. So the flame is phenomenally two dimensional. From the top you can see the flame covering the entire injector plate uniformly, and there is no side effects here, no side effects. So this is a phenomenal 2D flame, and in this front view you can see this is a boundary layer type flame. A boundary layer typically looks like that. So it also resembles a boundary layer. So boundary layer type flame. Okay. So this is the configuration. So by adjusting the air flow rate and fuel flow rate, we can make the extent higher and burning rate higher and so on. So all sort of control is possible, because whenever you have a separate flow rates for oxidizer and fuel, we can have better control. Okay. So as I told you, horizontal injector is used to send in the LPG, and air is supplied perpendicular to the stream. So it's again uniform flow of air comes in, and a boundary layer type of flame is formed like this, boundary layer resembling the boundary layer shape. Okay. Now if you see the characteristics of this, you can see that in the front part you can see blue region. Because of the incoming air, fresh oxygen is available and proper mixing takes place. A blue flame is formed here as shown by the front view and top view. So flame is bluish in color. Whenever you see bluish flame, proper mixing has happened in that. Okay, and it is relatively non-luminous. Then when you go further downstream, you can see that the luminous flames, you can see a bright radiation because of the soot formation and other things. Okay, bright radiation is formed here. Okay. Then based upon the air flow rate etc., fuel flow rate, air flow rate etc., we can see that the soot which is formed may be oxidized within the flame itself, or it may come out of smoke and so on. But anyway, please understand that here the air supply is very nice. So more control is available in the cross flow flames. But on the other hand, the stability of these cross flow flames also are restricted. We cannot have much even for example the flame which is formed like this phenomenally 2D flame which it may separate from one end and both ends and so on, forming some instabilities which I will demonstrate later. So, but this is another type of configuration which we will use to have better control of a diffusion flame. This is also a diffusion flame where cross flow reactants are injected. Now, the opposed flow or a counter flow. So, again please understand there are two ducts, as I told you, two ducts, one for fuel and opposing that another duct for oxidizer. Okay. Now, a flame is formed somewhere here. So, when two ducts are kept opposed to each other, there will be a stagnation zone. So, based upon the momentum of this fuel and momentum of the oxidizer, a stagnation zone may be formed, and based upon this stagnation flame, the flame will be formed somewhere in between these two. So, they say the separation distance is say L, somewhere in between 0 to L, okay, we will form a flame, and this flame is flat. Okay. So, this is the typical flame what we see here. This is a typical flame here, flat flame which is formed in between the ports. This is duct which is supplying oxidizer and this is duct which is supplying fuel and so on. Okay. So, almost a flat flame is got. See, basically the flame will form, and due to buoyancy the flame may rise up towards the end. Wherever the stagnation zone, the stagnation plane is intact, the flame will remain flat there. So, away from the stagnation plane, you will see that the flame will rise up due to buoyancy, or you can also take the hot gas from the, suck it down and take it through another port. So, it is also possible. So, in all together we are interested in the region here where the flame is flat, and we can take measurements of temperature, species, etc. Okay. Now, what is the advantage of this flame? This flame is extensively used in kinetic studies. So, when you want to do any chemical kinetics, this type of diffusion flame will be used. Okay. So, the flame is normally bluish in color. Methane itself is bluish in color. Here, due to the opposed flow, we have a good amount of mixing happening between the fuel and the oxidizer. So, you have a very good, so due to thorough mixing, a proper blue flame is seen. Okay. So, based upon the momentum of the fuel and oxidizer jets, we can position the flame anywhere. So, if we increase the fuel flow rate, then the flame will go towards the oxidizer side, and on the other hand, if you increase the oxidizer flow rate, then the flame will come towards the fuel and so on. So, we can by controlling the flow rates, we can position the flame anywhere. But if we increase the flow rates too much, the flame will not sustain, it will put off, it will extinguish, because the flame is stretched too much. So, that is called strain rate. Okay. The strain rate is increased beyond a limit, the flame will put off from the center and it will just blow off, that is it. So, again that is important. So, any extinction, that is very important to understand, and when you do careful experiments of fuel and with different fuel and oxygen flow rates with the momenta, we will calculate strain rate in a given manner, and once you know the strain rate, we can know at what strain rate the flame is put off, and that will be termed as extinction strain rate, that we will also see later. So, this is the configuration called opposed flow diffusion flames. Okay. Now, till now what we have seen is the gaseous fuel forming the diffusion flames, but when you have condensed fuels, whether it is a solid or liquid fuel, when you try to ignite the surface, then you will get diffusion flames formed over the surface. Okay. So, you can see the diffusion flames are formed over this, because now the for example, if it is solid fuel, it may pyrolyze to form vapors, gaseous fuels, and that gaseous fuel will mix with the oxidizer and form a flame. So, again you can see that there is no way to mix gaseous oxidizer in a liquid or a solid, correct. So, predominantly you will see diffusion flames are only formed. Okay. So, some examples are given here. Very important example is candle flame. So, candle, you can have a wax which is the fuel, and wax has a wick which is attached to this in its body. Then when you ignite it, what happens is the flame heats up the wax, creates a small cavity, and the wax is molten wax is present there, and the surface of the molten wax basically evaporates, and and also the surface of the wick is also having this to the capillary. The molten wax will come to the wick surface, and that will be heated up by the flame, and the vapors are formed. That vapor will travel from the wick surface. So this is the wick of the candle. Fuel vapors will form travels to this. This is the flame which is surrounding that, and oxidation from the ambient will come towards this, and a flame is formed wherever these mix in the stoichiometric proportions. Okay. Now the second example what is given here is called porous sphere flame. Okay. Now I have a injector or maybe a needle in which a porous sphere is mounted, and this porous sphere, the needle goes till the center of the porous sphere. So now this is the porous sphere. Now what happens when you supply fuel here, liquid fuel, the fuel goes to the surface and keep the surface saturated with the fuel, liquid fuel. Then when you can also have a airflow past this. When you ignite, what happens is a flame forms over the surface which is shown here, and you can see that the fuel will evaporate, the heat from the flame will be transferred to the film which is formed over the porous sphere, and this film will evaporate. Once it evaporates, more film will come, more fuel liquid will come to the surface. Okay, but the vapor which is evaporated here goes to the flame, and oxygen from the ambient comes from the atmosphere towards the flame, and a diffusion flame is formed. So this is the typical diffusion flame. Now we have a liquid pool. So for example, you have a liquid pool. Okay. Now if you ignite it, a flame will be formed like this over this. So this is what a typical flame. It's a slot burner here. A slot having a liquid fuel. Okay. So the surface is open to the atmosphere. When you try to ignite this, a flame will be formed. So please understand that for the flame to appear here, the temperature of the liquid surface should reach the fire point. Once fire point is reached, a diffusion flame will sustain over the surface, and then you can do the you can see the rate at which it burns basically. So once the flame forms over the surface, a diffusion flame forms over the surface here, you can see that fuel is transported from the surface to the flame, and oxygen is transported from the ambient to this, and the flame sustains like this. So here is a long and low width slit or a slot burner. So where the fuel is fed at the rate at which it is consumed. So steady flames. Please understand that these cases are steady flame cases where the fuel is fed at the rate at which it is consumed. So we can also have transient flames and so on. So these are the examples for diffusion flames which are attached over the condensed fuel surfaces.